14,000 miles of steel cables have supported the weight of the Brooklyn Bridge for more than 100 years of continuous operation. Why is this specific manufacturing process capable of producing strands that carry such colossal structures without failure? One might assume that the strength lies solely in the thickness of the metal, but in reality, the resilience required for these life-or-death missions is the result of a precise metallurgical journey that begins deep within iron ore mines. The process is only gaining momentum as the raw material reaches the steel mill for its primary transformation. Blistering temperatures inside the furnace melt the metal and its specific alloys into a uniform liquid state. One can notice how the heat-resistant equipment pours the white-hot mixture into molds to be cast into heavy billets. These solid blocks of steel represent the first physical stage of the future cable, yet they are far from the finished product. Everything only gets more complicated as the billets undergo a series of rigorous technical inspections to ensure no internal voids or structural weaknesses exist. It seems simple to just shape the metal, but the transition to the next level requires extreme mechanical force. Automated machinery draws the inspected steel through a sequence of dies, gradually reducing its diameter while increasing its tensile strength until it becomes individual wires. The equipment moves with calculated speed as these wires are then twisted together using high-tension rotating bobbins to form the final multi-strand cables. It is visible how the lubricants coat the moving parts to prevent friction during this high-speed braiding operation. Intricate operations involving massive machines ensure that the finished twisted steel can endure decades of service in the harshest environmental conditions. The technical details of each rotation and the chemical composition of the melt determine the reliability of the projects served around the world. This complex sequence of industrial steps explains how a simple raw material is transformed into a critical structural component. The material reaches the standard ready for the further stage of global distribution. 180 years ago, the first steel wire ropes emerged from the darkness of deep German mines. Why did engineers in the 1830s suddenly abandon traditional materials? The hemp ropes previously used in shafts had reached their physical limits and could no longer withstand the increasing mechanical loads of deep-sea extraction. But after one single successful replacement with metal strands, mine hoists gained the ability to descend hundreds of meters into the earth with significantly higher safety margins. This transition effectively removed the barriers to large-scale industrial mining across the continent. Nearly 200 years have passed since that first application, and the material has now saturated every conceivable industrial field. One can notice how its presence has become a fundamental requirement for modern infrastructure and heavy manufacturing. 10 million tons is the approximate volume of steel cable the world consumes every single year. These massive quantities are distributed through critical sectors, including oil and gas extraction, international shipping, and the burgeoning field of renewable energy. Millions of elevators in every corner of the globe depend entirely on these cables to function. Without this specific technology, skyscrapers could not rise to their current heights, and the very skyline of modern cities would remain flat. It only looks obvious that a thin wire can hold such weight, but the internal mechanics are far more complex. At first glance, the cable is a simple industrial component, but in reality, the true marvel lies in the ratio between its small diameter and its immense load-bearing capacity. The equipment gradually twists bundles of individual steel wires into a tight, cohesive structure. This specific geometry does not just provide the necessary flexibility for winding onto drums. It ensures that the mechanical force is distributed with absolute uniformity across the entire cross-section of the rope. A cable measuring only a few centimeters in thickness can support a weight of several hundred tons without failing. The process is only gaining momentum as new alloys are introduced to the twisting machines. One can notice how each wire stays in its calculated position, contributing to the collective strength of the bundle. Everything only gets more complicated when considering the fatigue limits of these metal strands under constant tension. The mechanical properties of the twisted steel allow it to outperform any solid rod of the same diameter. Thus, the material reaches the standard required to support the weight of the modern world. One of the key stages in the history of structural engineering concludes with this realization, as the transformation of simple wire into a high-capacity cable is complete. Thousands of feet below the surface of the Earth, the initial journey of a steel cable begins within the dark corridors of massive underground iron ore mines. High-power drilling systems bore into the solid rock with mechanical precision to create deep vertical channels for the placement of explosive charges. Why is such a violent method of extraction necessary for the production of flexible wire? It only looks obvious to simply dig the material out, but in reality, the iron ore is trapped within a reinforced geological matrix that requires a sudden release of energy to break the molecular bonds of the surrounding stone. One can notice how the rock face shatters into manageable fragments following a sequence of controlled detonations, which effectively release heavy blocks of reddish-brown iron ore. Enormous hydraulic excavators move into the dust-filled chambers to lift individual boulders weighing dozens of tons with a single tilt of the massive bucket. The process is only gaining momentum. These mechanical giants load the raw material onto mine trucks, capable of carrying payloads of several hundred tons across their reinforced axles. One can notice the slow, rhythmic compression of the heavy-duty suspension as each bucketful of rock is deposited into the cargo bed. These trucks move continuously along dedicated, high-capacity routes to transport the ore out of the deep pit and toward the surface processing facilities. But this is just the beginning. The ore is dumped into massive steel hoppers at the primary stockpile area before being transferred onto industrial conveyors stretching for hundreds of meters across the landscape. Along these moving belts, vibrating screens and magnetic separators work in tandem to strip away dirt, sand, and other coarse impurities that would compromise the chemical purity of the future melt. It seems simple to just move the rock, but in reality, these separators must catch every non-metallic fragment to ensure the integrity of the steel. The pre-processed ore then enters a series of primary crushers where it is reduced to significantly smaller sizes. This mechanical reduction makes the material easier to manage during high-speed transport and subsequent smelting in the blast furnaces. Everything only gets more complicated as the logistics chain expands. Specialized rail wagons and massive bulk cargo ships take over the next phase of the journey, with each vessel hauling tens of thousands of tons of material across oceans and continents. This entire cycle of extraction and initial refinement runs without a single pause in operations. Such relentless movement ensures a steady and predictable supply for the global steel industry, guaranteeing that enough raw material is always available for the complex stages of cable production. The mineral wealth of the Earth is thus prepared for its transformation into high-strength wire. 1,500 degrees is the starting point for the thermal transformation of raw ore into industrial steel. As the heavy ore trains come to a halt at the steelworks, the smelting process is initiated with the unloading of thousands of tons of iron ore. Why is recycled scrap metal added to the virgin ore at this stage? At first glance, it might seem like a simple additive, but in reality, this mixture optimizes the melting efficiency and chemical properties of the final alloy. The combined material is fed into an enormous electric arc furnace that stands as tall as a multi-story building. Inside the chamber, giant graphite electrodes channel immense electrical currents directly into the heart of the pile. This generates a localized heat that exceeds 2,900 degrees, a temperature high enough to liquefy solid metal into a swirling, incandescent mass. One can notice how the melt begins to glow with the intensity of volcanic lava as it shifts within the furnace. To achieve the specific mechanical properties required for high-strength applications, engineers introduce precise quantities of alloying elements. Manganese is added to increase the overall strength of the lattice. Chromium and nickel are injected to provide essential corrosion resistance, while silicon is utilized to enhance the metal's ductility. Simultaneously, the technicians introduce quicklime and fluorspar into the liquid bath. These agents react with the impurities to form a layer of slag that rises to the surface like a thick gray foam. Everything only gets more complicated. This slag acts as a technical filter, absorbing unwanted elements and refining the molten metal to ensure it is both cleaner and structurally sounder. Massive electrodes rotate ceaselessly to stir the mixture, ensuring a homogeneous distribution of the alloys. Modern sensors monitor the chemical balance with millisecond precision, verifying that every batch meets the exacting standards of the facility. Once the steel reaches the required purity, it is moved toward the casting stage. Transition to the next level. Unlike the traditional methods of pouring batch by batch, the facility employs a continuous casting system. The white-hot steel flows into copper molds that are equipped with high-capacity forced water cooling systems. As the liquid metal makes contact with the chilled mold walls, the outer shell solidifies instantly. One can notice how the core remains molten even as the exterior hardens into a solid shape. Solidification fabrication progresses from the outside inward, eventually forming solid billets several meters in length. These billets typically possess a square or rectangular cross-section. Immediately upon exiting the mold, they remain at temperatures of several thousand degrees. To take advantage of this retained thermal energy, they are sent directly to the primary rolling mill. But this is just the beginning. Massive alloy steel rollers, some measuring several meters in diameter, rotate continuously to receive the glowing billets. These rollers apply immense mechanical pressure, flattening and elongating the metal with every pass. With each successive transit between the rolling stands, the thickness of the billet is reduced while its length increases significantly. The high internal temperature keeps the steel ductile, allowing it to deform under pressure without developing surface cracks. The repeated mechanical forces realign the internal grain structure of the metal. This makes the steel more uniform and stable before it enters the wire drawing stage. Following the hot rolling phase, the semi-finished products are diverted to the cold rolling line. Here, they will be drawn into wires with precise dimensions. The process begins as the glowing bars are subjected to a high-pressure water spray system for rapid cooling. It gets more complex further on. The steel then passes through a series of rolling stands where large alloy rollers apply massive force to thin the material. With each pass, the square or rectangular section is reshaped into the round or flat forms necessary for drawing. In the wire drawing stage, the steel is pulled through a succession of dies with progressively smaller diameters. Each pass makes the wire thinner and the surface smoother, while the internal structure becomes increasingly dense. This stage is conducted at room temperature, requiring absolute control over the pulling force and the friction between the steel and the die. Why is the speed of the pull regulated so strictly? A single deviation in tension can cause the wire to break or lose the ductility required for the final product. Laser sensors are installed along the line to measure the diameter of the wire in real time. These sensors are paired with automatic feedback systems that adjust the pulling force instantly to maintain dimensional accuracy. The result is a high-strength steel wire coil produced with near-perfect tolerances. Reaching the desired dimensions, however, is only half of the journey. To meet the necessary mechanical standards, the wire must undergo a harsh heat treatment. The wire is fed into a specialized furnace and heated to temperatures ranging between 700 and 1,500 degrees Fahrenheit. The atmosphere inside the furnace is tightly controlled. The heat turns the wire a glowing red and alters its internal crystal structure. This realignment of the metallic grains provides the ideal balance between hardness and flexibility. As soon as the target temperature is reached, the wire is guided out of the furnace and into the quenching zone. One can notice how jets of high-pressure air, or baths of specialized industrial oils, rapidly cool the steel. This thermal shock locks the newly formed grain structure into place. Immediately after the heat treatment, the wire enters the anti-corrosion coating phase. Depending on the final application, each strand is covered with a protective layer of zinc galvanizing or a polymer coating. In environments exposed to moisture or salt water, this layer serves as a physical shield against oxidation. Before the coating can be applied, the wire is cleaned in a mild acid solution to remove dirt, grease, and microscopic rust. The wire is then dipped into a bath of molten zinc. Both temperature and pressure are tightly controlled to ensure the coating is uniform and free of air pockets. Even the smallest gap in the coating can cause the wire to deteriorate rapidly when deployed in the field. The process is only gaining momentum. The inspection stage serves as the final trial for the material. Under the scrutiny of advanced sensors, every flaw is revealed, from geometric distortions to surface warping. The diameter must be accurate down to small fractions of a millimeter. Data from each individual wire is recorded and compared against strict technical benchmarks. If any irregularity is detected, the wire is immediately removed from the line to ensure only the highest quality product moves forward. After passing inspection, the wires are transferred to the stranding line. Here, they will be twisted into a complete cable structure. The stranding system utilizes dozens or hundreds of wire spools mounted on massive rotating frames. One can notice how these frames rotate rhythmically around a central axis, pulling the wires under tension and twisting them into a helical pattern. Engineers first determine the appropriate core type for the cable. The core may consist of steel for high tensile loads, or synthetic fibers like polypropylene for lighter, corrosion-resistant applications. The wires are grouped into strands, and then multiple strands are twisted around the core to form the finished cable. Throughout this operation, sensors monitor the tension and vibration levels continuously. If any wire is pulled too tightly, the system automatically corrects the tension in real time. The stranding speed is also regulated to prevent deforming the wires. Once the first layer is complete, the machine winds successive layers according to the preset design. Each layer serves a specific function, such as resisting abrasion or bearing the primary load. The finished cable is flexible enough for installation, but strong enough to support hundreds of tons. However, the cable cannot be deployed without its final layer of lubricant. This specialized oil is applied by immersion or high-pressure spraying to ensure deep penetration into the grooves. Flow and temperature sensors regulate the amount of oil used to maintain a consistent viscosity. For marine environments, the oil is enhanced with additives that protect against electrochemical corrosion. The molten stream of protection ensures the longevity of the mechanical performance. Thus, the steel reaches the standard ready for the further stage. 600 tons of hydraulic pressure are applied to the cable segments during the final stage of quality control. Why is such extreme force necessary after the protective lubrication process is already complete? It would seem the cable is ready for the field, but without verifying the ultimate breaking point, the safety of the entire industrial application remains an unknown variable. This destructive testing ensures that every millimeter of the metallic structure can endure the harshest real-world conditions. Large-scale hydraulic tensile machines pull the material continuously until a complete structural failure occurs. During this process, one can notice how microstrain sensors detect the slightest elongation in the steel strands. This allows engineers to determine the true load-bearing limit with mathematical certainty. But this is just the beginning. Cyclic bending rigs then take over to simulate severe operating environments through thousands of repetitions. The cable is twisted and bent under varying pressures to mimic the mechanical stress of cranes or suspension systems. The process is only gaining momentum. Any sign of irregularity, from microscopic cracks to minor inconsistencies in structural uniformity, results in the immediate rejection of the entire batch. Only the cables that withstand every one of these rigorous tests are cleared to move forward toward the packaging zone. Once the quality is approved, the cable is fed into a high-speed industrial coiling system. At first glance, the winding seems like a simple mechanical rotation, but in reality, it requires constant synchronization of speed and tension. A central controller and specialized load sensors regulate the feed to ensure the wire does not slacken or overlap unevenly during the loop formation. The camera glides along the rotating turntable, which works in perfect sync with a transverse guide rail. This mechanism places each loop of cable precisely into its designated groove on the spool. On advanced production lines, integrated displacement sensors and high-resolution cameras detect and correct any winding deviations in real time. It gets more complex further on. The equipment gradually slows as the coil reaches its full capacity. Hydraulic clamps are then used to secure the ends of the cable firmly against the reel. Traceability codes and comprehensive batch data are printed directly onto the coil core to ensure a permanent record of the manufacturing history. Transition to the next level. Each finished coil is mounted onto heavy-duty steel or engineered wood pallets for stability during transport. To prevent any environmental degradation, the units are tightly wrapped in heat shrink film or specialized oilcloth for moisture protection. One can notice the precision of the automated cranes as they lift the pallets into the high-ceiling storage area. Forklifts eventually move the secured loads to the logistics zone for final dispatch. The coils are placed onto flatbed trucks or into specialized containers equipped with anti-roll compartments. This ensures the material remains stationary throughout the journey to the end user. The molten and drawn steel has now reached its final commercial form, ready to leave the factory. 150 tons of raw steel undergo a complete transformation into high-strength industrial cable. Why must the metal pass through such a complex series of thermal and mechanical transitions? A simple block of alloy cannot withstand the tension required for suspension bridges or heavy lifting gear. Only through precise structural reconfiguration does the material acquire its final properties. At first glance, the process looks like a simple reduction in diameter, but in reality, every millimeter of stretching is monitored by automated laser sensors. It is visible how the cooling systems spray a constant mist of lubricant over the rotating dies to prevent microscopic cracks. The process is only gaining momentum as the wire moves through the drawing machines at a speed of 20 meters per second. One can notice how the metallic surface gains a polished, silvery sheen during the final stages of cold deformation. The equipment gradually winds the finished strands onto massive wooden or steel spools with a pulling force calculated to the pound. Everything only gets more complicated when multiple wires are braided together to form the final cable core. Because each individual filament must share the load equally, the tensioning during the winding process is maintained with absolute absolute consistency. Therefore, the finished product stands as a physical manifestation of modern engineering precision and industrial power. This concludes the current stage of the production cycle as the material prepares for heavy-duty applications. Thus ends one of the key stages of high-strength steel manufacturing.